Well, hey everyone, Mrs. Hanson, one more time in Chapter 18. We're going to conclude our lessons today talking about ammonium salts along with their nomenclature and solubility rules. You'll have an opportunity again to do some reading with sections on medicine and health applications. We have some practice problems kind of pulling it all together on our agenda as well. So let's begin looking at ammonium salts, the product of an acid-base reaction. So as an example, the product of a reaction, just kind of getting us back into the groove of what we're looking at, propane amine, which would be propylamine for a common name. I can see that I would have, and this actually should have a 1 propane amine, giving us a locant for IUPAC. And the common name is using the alkyl, letting us know that the amine is at the terminal end. So here we have propylamine as a common name, or 1 propane amine, and we're going to react that with HCl. Just a little review from our last section, where we've learned that amine-based compounds act as a base, and an acid will neutralize a base, forming a salt-water solution. An aqueous salt will form. The nitrogen's electrons, the lone pair, very rich in electron density, reach out for this proton and this bond collapses. That is the definition of proton transfer in acid-base reactions. So on the product side, we would have our propane amine giving us the nitrogen still attached to those 2 hydrogens. And now leading up to a 4th bond, we know that that is a quaternary nitrogen, meaning that it must be positively charged, and the anion that would form is negative. So conjugate pairs, the conjugate acid and the conjugate base, are the resulting species from a proton transfer. We'd like to explore a little more about these ammonium salts, practice naming them, and discuss their solubility. So again, these are ionic compounds. Ionic compounds are made of positive and negative ions. The positive ion is the cation from the ammonium derivative, and the anion is the conjugate base from the original acid. Now, let's practice naming those in terms of how we go about finding a name. So the original name on the amine, propane amine, or propylamine. That was fine too, wasn't it? Based on that being a primary amine at the terminal end, so we could name it with a common name as well. To name this as a salt, I want us to just take off the word amine, and we're going to replace it with the polyatomic name ammonium. And I'm doing this in terms of IUPAC in this example, or we could certainly express it with the common name in this first example as well. So I've just named this cation as 1 propane ammonium or propylammonium. And if I wanted to include its last name for the salt, it would be chloride. The name of my salt that formed from the neutralization of my acid and base would be called 1 propane ammonium chloride for its IUPAC name, or propylammonium chloride for its common name, because our common name is acceptable with primary amines that are located at the terminal end of the chain. So we're going to practice a little bit more with naming salts. And just to remember, to name a salt, we're going to name the ammonium salt by identifying the 4 groups that are bonded to the nitrogen atom. That is a quaternary nitrogen. Quaternary nitrogens are always positive ions. Remove the hydrogen from the N and draw it as the structure of the parent amine, and then just simply put the 2 parts together. The ammonium ion receives the suffix ammonium in place of amine, and then just add the name of the anion. Let's practice, because those rules seem like there's a long set of rules, but it's really not. How would you name the salt is from the parent amine? That's all we're really looking at, changing the word amine to ammonium. Let's try it. Here I have the positive and a negative ion, and that's the definition of a salt. Since it's in a nitrogen-based salt, it's called an ammonium salt. The nitrogen is attached to 3 hydrogens and a 2 carbon group. So the positive, just kind of looking at its structure, and then the negative ion here, Cl negative. So let's work this through. How would we name the salt? Well, in other words, I want to just ignore the 4th bond for now. For now, just ignore this and name it as an amine. So this would sound like ethylamine or is a common name, or IUPAC name for this would also be called ethane amine. So I'm naming the parent amine. That's step 1, name the parent amine. To turn it into the name of the salt, you're going to take off the name amine and you're going to put on the last suffix here, ammonium. And then to name the salt, you'll name the negative ion. Cl negative is named chloride. So this salt, for letter A, has a common name called ethyl ammonium chloride. And those are 2 separate words. That's your common name. Or its IUPAC name would be ethane amide. Oh, it's not amide. Ethane ammonium. There, I caught it. Chloride. And again, I'm just giving it 2 names so you could definitely hear a common name is very appropriate in this example, but absolutely every compound can always have an IUPAC name as well. Ethyl ammonium chloride or ethane ammonium chloride for letter A. Well, let's look B over. Letter B has nitrogen attached to a hydrogen and 3 methyl groups. So that right there, again, it's a quaternary nitrogen, so you can see it has a positive charge. But to name this, we want to work and find the parent amine. So ignore the NH branch first. Ignore the 4th bond to name the parent amine. The parent amine in this case would be trimethylamine. And that, because all 3 groups are the same, that is its IUPAC name. So if the parent amine is trimethylamine, to name it as a salt, you take off amine and you put on the last name ammonium. And then we name the last negative ion as well, CH3COO negative. I want you to think about what that came from. This is the negative ion from the carboxylic acid, acetic acid. So this is called the acetate ion. And then we want you to just remember back to a previous chapter on carboxylic acids. Cool, hear that? That the CH3COOH, that's the carboxylic acid, it had a name of acetic acid. And we learned that you take off the ic and you put on 8 when you're naming its negative ion. Acetic acid becomes acetate polyatomic ion, and that's exactly what we have here. So the name of letter B, putting it all together, trimethyl acetate. Whoops, trimethyl ammonium acetate. How'd you do? Well, that's a good start, and I know it takes a little bit of practice, and let's do that right now. Let's just practice naming each salt, and when you're ready, come back. Give yourself think time, pause the video, check these out, and then come back to me when ready. All right, awesome. Let's try these out. Let's do letter A together. I have a nitrogen attached to 3 hydrogens and attached to a methyl group. So its name would be either methane ammonium chloride or methyl ammonium chloride. Now let's review how I got that. Remember, it said to ignore the 4th bond and find the parent amine. Ignore the 4th bond and find the parent amine. The parent amine would be called methane, and then lop off the E and put amine, or methylamine. It has a common name as well as an IUPAC. So this would be common, and this is the IUPAC name. We've learned to take off amine and put ammonium to name that polyatomic ion. So methane ammonium chloride or methyl ammonium chloride is the name of the salt in letter A. Let's try B. In letter B, I have a nitrogen attached to 2 hydrogens and a 1, 2, 3 carbon chain in both directions. So 1, 2, 3, 1, 2, 3. Ignore one of the hydrogens and name the parent amine. Since I have a parent amine that is a secondary amine and both of the groups are exactly the same, we would name that dipropylamine. A secondary amine where both groups are identical. And that means the IUPAC name is dipropylamine. Now, to name it as the ion, we take off amine and we put ammonium. And then just name the last negative ion as bromide. That becomes dipropylammonium bromide. All right, we got one more to check. Letter C. Here's the nitrogen. Let's see what we have going. The nitrogen is attached to 1 hydrogen, 2 methyl groups, and an ethyl group carrying a positive charge, right? So anytime you have a 4th bond, you know it's a positive charge. And its last name, CH3COO negative, that's the acetate polyatomic ion coming from acetic acid, which is a carboxylic acid, acetate. We have to remember that. So let's find the parent name of our amine, right? So this first step, ignore the 4th bond, ignore it for now, and just name that amine. So here we have a tertiary amine. The longest carbon chain is ethane, 1, 2. We have 2 methyl groups also. So this will involve an N, N dimethyl And then the 2 carbons are ethane. And then you'd have your amine, but I'm going to turn that into ammonium and then acetate. NN, dimethyl, and you could actually have a common name there as well. Because that carbon that there is perfectly fine to put the common name of ethyl ammonium acetate. But this is the better, it's an IUPAC name. I wouldn't even say let's just throw out that common name and just stick with what we know, IUPAC. NN, dimethyl. It would have been ethane amine. I took off amine and put ammonium. That's ammonium acetate. There's a lot of letters in those names, aren't there? Really, I just want to focus then on just practicing naming amines, and then naming ammonium problems really come out just to be quite easy. We're just exchanging the word amine into the word ammonium as the suffix. So the solubility of ammonium salts, we've recognized that ammonium salts are always water soluble. I don't care how long the carbon chain is, ionic compounds are water soluble salts. Amines that contain fewer than 6 carbons are soluble in water. They have enough of a polar region where they can be water soluble. Amines containing more than 6 carbons have a nonpolar region that's too great, and so it is insoluble. And remember that ionic salts are always, always, always soluble. And you'll be just asked to recognize, based on the structure of the amine or the structure of the ammonium salt, if it is water soluble. And as we think about just kind of an example, and there's nothing to write, it's just kind of a visual. Here we have octylamine. Do you notice that this would be 1, 2, 3, 4, 5, 6, 7, 8 carbons in an octylamine? Well, certainly that's greater than 6, so this is an insoluble amine. Carbon chain is too long. This is a very nonpolar region, making that an insoluble amine. Even though this is a polar region, we're saying that the carbon chain has become so long that it dominates the qualities of that molecule and makes it an insoluble compound. However, if I treat that with an acid, we can form a salt, right? Because a base plus an acid produces a water-soluble salt. So I'm able to convert my insoluble amine into a water-soluble salt. And we would call that octylammonium chloride. We have a positive cation, a negative anion, that's the salt, and salts are always soluble. Does not depend on the length of the carbon chain. Label each compound as water soluble or water insoluble. How about letter A? Well, letter A has a nitrogen attached to 2 carbons in 3 directions. Right? So this would be triethylamine. And the rule says to be water soluble, you have to have less than 6 carbons. So therefore, that is 1, 2, 3, 4, 5, 6 carbons, making this insoluble. Letter B, well, look what we've done. We've turned that into a salt, haven't we? Letter A, turning into letter B, adds a hydrogen to that bond, creating a positive, and then of course it has to have a negative name as well. You would have triethyl ammonium bromide in letter B, trimethyl ammonium bromide. That's the name of the salt in letter B, and salts are always soluble. Letter C gives us a primary amine with only 2 carbons. Well, that would make that soluble. And in letter D, oh look, I have a salt. I have a positive ion and a negative ion. That's an ammonium salt, and they are always soluble. Easy enough. Good work. These ammonium salts can convert back to their amines by treatment with a base. So really, we're just reversing the reaction in acid-base chemistry. So let's let the ammonium salt act as the acid and treat it with the base. Now, of course, the sodium is going to be what we call a spectator ion. So just really focus on the base being OH negative. And here is the proton on the ammonium salt. The base, and this is the mechanism, the base reaches out for the proton. This bond collapses. So the OH negative acts as the base, reaches out for the proton, and now look, this right here is the conjugate acid of OH negative. This is the base. Here is its conjugate acid, water. And notice that the chloride also really is nothing more than a spectator ion. The spectator ion of sodium and the spectator ion of chloride will just group together based on electrical charges of opposites. Sodium chloride would be the salt that forms. And of course, this bond collapsed, giving a set of dots to the nitrogen. So you had a quaternary nitrogen cation go back to form a tertiary amine, the water and the salt that forms. So we practiced with octyl ammonium chloride, which would be a water-soluble salt being treated with a strong base. Again, it's just proton transfer. All we have to do is understand Bronsted-Lowry theory from Gen Chem days, and we've got this mastered. The base removes a proton, going back to the tertiary amine, and forms conjugate pairs. Let's try one on our own. You try writing out propyl ammonium chloride, treating it with a strong base, and showing the formation of the products, modeling after the octyl ammonium example I just worked. Are you pausing your video? I'll assume you paused and are ready to come back. So let's take a look at propyl ammonium chloride. Well, propyl means I have a 3-carbon chain attached to a nitrogen. And of course, we have a hydrogen, making it a quaternary compound. And that's a positive charge up here. And of course, the chloride is the negative ion. And I'll just write it there, Cl negative. There's our salt, propyl ammonium chloride. Chloride is a spectator. It's not really doing any acid-base chemistry at all. And the sodium is the spectator as well. It's not participating in the acid-base chemistry at all. It's just there to neutralize charges. So when I look at NaOH, that is a strong base, and the salt is going to act as the acid. The acid donates a proton and the base accepts the proton. So when you think about hydroxide, draw that as OH, and it's a negative charge. The negative charge means it's very electron rich. So it's attracted to the positive proton based on its negative charge. Now the reaction arrow would show the water, the oxygen itself, reaching out for this proton, forcing this bond to collapse onto the nitrogen. So the propylamine that forms still contains 3 carbons attached to the nitrogens, and that has 2 hydrogens, and the bond turned into a set of dots. This is the conjugate base of propylammonium chloride. The conjugate acid of hydroxide is your water molecule that formed. When OH accepts a proton, it forms a conjugate acid. And of course, the sodium, which was part of the base name originally, and the chloride, which was part of the salt's name originally, will just migrate together based on opposite charges. But again, they're not really part of the chemistry so much as just keeping things neutralized in charges. So those are referred to as spectator ions. Are you ready to try some on your own? What product is formed when each ammonium salt is treated with sodium hydroxide? Pause your video and give yourself genuine think time. All right, welcome back. Let's see what we have. The ammonium salt in letter A. We had a nitrogen that's attached to 3 groups of ethyl and a hydrogen. So this would be called, just to practice your nomenclature, triethyl ammonium. And what last name do we have? Oh, we have a bromide. So there's the Br negative. And we're going to react that with sodium hydroxide. A proton will transfer. Now just think about the sodium ion and the hydroxide ion. They're not really together, just based on electrical charges. They're near each other, but they are going to act individually. So just recognize, we can just highlight, the bromide and the sodium do not participate in this acid-base proton transfer. They will just migrate to each other and form the salt called sodium bromide. Spectator ions, they just land together based on opposite charges, not part of the proton transfer. The proton transfer originates at the base, and it plucks off the excess hydrogen on that amine group, and this bond collapses. So in terms of the amine that forms, we have nitrogen. Now, instead of a 4th bond, it's back to a set of dots. And we have 2 groups, or 2 carbons on each other end of those bonds. So this would form the conjugate base. So here is your acid. Here is your base. The conjugate acid is now just simply named triethyl amine. You also have the conjugate base of hydroxide, which is water, and sodium bromide. Triethylamine plus water plus sodium bromide. Those are your products formed. Of course, the salt, triethyl ammonium bromide, converted back into the original amine, and a water and a salt with treatment of the sodium hydroxide. Let's talk through the mechanism, with letter B. Pardon me. Letter B gives us a 2-carbon chain leading to nitrogen, and it's leading out to 3 directions of hydrogen. And of course, it would have a positive charge. It has a last name of hydrogen sulfate. That's its salt name, hydrogen sulfate. And we're going to treat it with sodium hydroxide. So here we have our salt. The salt cation is going to act as the acid. And I want you to just really think that through, that the hydrogen sulfate and the sodium are spectator ions. They do not participate in the proton transfer. So you can just figure that out already and write them on the product side. That you will have a sodium hydrogen sulfate form, because those positive and negative ions are just going to migrate together. It's the cation that acts as the acid. It's the anion that acts as the base. And a proton will be transferred in the following way. The hydroxide, OH negative, originates with its very electron-rich oxygen, originates the transfer. And it's going to remove one of those 3 hydrogens. It can be any one of the 3. It doesn't matter. They're all equal. And then a bond will collapse. And when that does, we come out with a 2-carbon, still leading to the nitrogen, and this bond turned into a set of dots, and the conjugate acid of the base forms. That's a water molecule. So here in our letter B, we had ethyl, ammonium, and then to name hydrogen sulfate. Just practicing nomenclature every chance we get as well. This was the salt that we started with, and it reacted with sodium hydroxide, and it formed ethylamine plus water plus sodium hydrogen sulfate. And those sodium hydrogen sulfate are just the positive and negative spectators ending up together based on opposite charges. A proton was transferred to get me back to the original amine, ethylamine forms, with treatment of a strong base. And you had one more to practice, letter C. This one gave us a 6-membered ring with nitrogen as that 6th member, leading out to 2 hydrogens. Remember that name from a pepper? Here's plus, and here's the negative. We're going to treat that with sodium hydroxide. So I want you to just think that through when you see the chloride. I didn't mean for a crayon, I wanted a highlighter. When I see the chloride and when I see the sodium, those are called spectator ions, and the salt that will form will be sodium chloride. Don't even bother with them in terms of acid-base chemistry. Focus on the proton transfer. The hydroxide acts as the base. The cation, the ammonium ion, will form as the acid. The base reaches out for the proton, and that bond collapses. That's your mechanism. So on the product side, you still have your 6-membered ring. And now instead of leading to 2 hydrogens, it leads to just 1 hydrogen and a set of dots. And the conjugate acid of hydroxide formed, which would be water, and the sodium chloride salt. And there's your acid-base reaction. When treated with a strong base, ammonium salts drive the reaction back to the original substructure. So we've done some good acid-base chemistry. At this point, you've got some reading to do. And at the very end of your pages, page 15, you'll come back and work some extra practice problems. How long have I been talking? about half an hour. I'm going to stop the video here, let you work in your notepad and complete it. What I'll add is kind of a last video where I work the example problems that say extra practice problems. I'll work those out, and when you're ready to check them, come back to find the next and last video of just kind of a solution guide to the extra practice problems. Do your reading first and then practice those ending problems. Come back to the last video when you're ready to do your final checking.